Good morning everyone. Today we are going to cover normal modes and small oscillations. We'll first try to understand these two terms, what are small oscillations and what are normal modes. हमने अपने डेली एक्सपीरियंसेस में कभी ना कभी ऐसे सिस्टम ज़रूर देखे होंगे जो एक पॉइंट के अराउंड ओसिलेटरी मोशन करते हैं. ओसिलेटरी मीन्स सम बैक एंड फोर्थ मोशन. फॉर एग्जांपल वी हैव ए रिजिड वॉल, a smooth surface, there is a spring and some mass is attached to this spring. This is its equilibrium position where it can rest forever if not disturbed. Let's call it x equal to x naught. What happens if we slightly disturb it? Let's say we extend this spring such that it bring the new position of this mass m is here. Let's say we displace this mass by delta x. Under this condition, if we release this mass, it will start doing some oscillatory motion about this point x equal to x naught. In Newton's equation form, we write it as, since we know that F net is equal to mass times acceleration, and let's say mass is m, acceleration we can write it as x double dot, and it should be equal to the force, and the restoring force that the spring would apply on this mass will be minus of k times x, where k is some spring constant. So under such equations we can also define some term known as angular frequency omega, and it is given by 2 pi times square root of k by m. So this is this expression, they are for very specific system like this, but can we generalize this problem? What is the underlying mathematics? What is the underlying physics behind all such problems? One more example that I would like to give is, let's say we have a bowl, there is a marble in it, and if we displace this marble little bit, let's say we bring it here and release it, then it will also start doing some oscillatory motion. Can we generalize this problem? And the underlying concept behind all such problems we'll see just now. So let's say we start from a one particle in one dimensional potential. Potential is, let's say, Vx, and suppose x equal to x naught. Okay, we'll define to later. Let's say we are interested only in the neighborhood of x equal to x naught. How this potential will look like and so. And to know that and to calculate that, we have a technique, a mathematical tool known as Taylor series. So we can write any given function. Here the potential energy V, we can write it around x equal to x naught. So x naught is some point, and we want to get its value if we displace the system from x naught by some amount delta x. It would be given as V of x naught plus V dash at x naught multiplied by delta x plus 1 by 2 times V double dash of this Vx function at x equal to x naught multiplied by delta x square, and plus some higher order terms. Since we are only interested in small oscillations, so we will ignore these higher order terms. First of all, this v of x naught is some constant value, so we can take it, we can assign it any arbitrary value. Let's say it is, we set it to be 0. It does not impact the overall problem. Second, we have v dash of x naught plus v double dash of x naught. But let's say, if we say that if x equal to x naught is equilibrium point, what do we mean by an equilibrium point? Equilibrium point, at equilibrium point, the net force on the system is 0. So F at x equal to x naught, it should be 0, and F for the conservative system, it is given by the negative of the potential energy. So here it will be minus of v dash x naught, and it should be 0. So the second term is also 0. So what we are left in the final is v of x naught plus delta x, it should be equal to half of v double dash of x naught times delta x square. Now let's try to understand this potential more. Let's say this v double dash of x naught, it is negative. If it is negative and we displace the system by some delta x amount, so delta x square, it will always be positive. So what we are finding is that if v double dash of x naught is negative, then potential energy of the system will decrease as we displace it. So जैसे ही हम सिस्टम को डिस्टर्ब करेंगे, लेट्स से x equal to x naught is our equilibrium point, and we displace it by some delta x amount, so this new energy here, this new potential energy here, it is lower than initial one. It is like, let's say we had a bowl first, the bowl was sitting on top of it, and if we displace it slightly, the new location is there, and in the new location the potential energy is lower than what was before. So under such condition, the particle will not do any oscillatory motion, it will just follow this trajectory and fall off. Okay, but what happen if v double dash of x naught is positive? If it is positive, it means that the new potential energy will be higher than what we started from, and so the system, ideally the system wants to minimize its lowest, its potential energy, so it will somehow try to regain its original position. So so we can correlate this v double dash of x naught to be positive from this case. Let's say we have a bowl, at the bottom we have a marble, and if we displace it, let's say when it goes there, and now it will do some oscillatory motion about this point x equal to x naught. So what do we learn from it? We learn two things, that for a system to perform small oscillations, the first condition is that we should have v dash of x to be 0 at that particular point, at that particular point. This is the first condition. Second condition is that v double dash of x, it should be positive, and let's say the particular point is x naught, so I am writing here specifically x naught. So these are the two conditions that must be satisfied for any system to perform oscillatory motion. Now let us try to understand it more in depth with the help of some problem. Suppose that we have a particle of unit mass which moves in a potential given by v of x equal to ax square plus b upon x square, where a and b are positive constant. We have to find out if this system will perform a small oscillation about any given point, and if it does so, then what will be its angular frequency. Let's see. So for a system to perform small oscillation, the first condition that is that the v dash of x, it should be 0 at any given point. Let's say some given point x equal to x naught, and that x naught will be then its equilibrium point, or we also call it at the mean position also. If we take the second derivative, it is 2ax minus 2b upon x cube, and let's say we are calculating it x equal to x naught, it should be 0, which implies that a x naught raised to power 4 minus b equal to 0, or we can write x naught equal to b upon a raised to the power 1 by 4. So at this point, the net force on the system is 0. But second condition for the system to perform small oscillation is that this v double dash of x, it should be positive. Let's calculate it. V double dash of x, it will be 2a, the derivative first term, plus 2b upon the derivative of x cube is 3 times x raised to power 4. And this thing we need to calculate at x equal to x naught. So the second derivative will be 2a plus 6b times b over a, so it will be 8a. Yeah, so it, and since it is given that a is positive, so this will perform small oscillation about this point. Now the very simple thing that we need to calculate is what is the frequency of the small oscillation. So frequency is given by 2 pi square root of k by m, where k is the second derivative at x naught, which is 2 pi square root of 8a, and mass is given to be unity, that is 1. So omega will be 2 pi square root of 8a. That is the final answer.